Hi, welcome back. This is another episode of Stefan Needs Another Project Like He Needs a Hole in the Head. I purchased a 3-axis fixed gantry CNC router mill machine frame. The story behind this is a company in Germany, CNC Technik Müller, makes these frames and larger ones. They are a welded steel construction out of sheet metal, and they are filled with epoxy granite. Epoxy granite is basically epoxy resin mixed with gravel. Well engineered gravel. You have to get the mixture of different grain sizes correctly to get a maximum packing efficiency between the grains of gravel to use as minimum epoxy as possible to get an as stiff as possible casting. Long story short, I didn't purchase the frame from them. I have no business with them. A friend of mine bought this years and years ago and never got around to work on it, so I asked him if he wants to get rid of it, and end of the story, it's sitting here in my own shop. Part of the story was also to build a table for the machine to sit on, and after doing a little bit of CAD work, I decided on using 60 by 60 by 3mm wall thickness square tubing. And since I'm not set up as a fabrication shop, I don't have a welding table or a horizontal bandsaw to cut long pieces of stock nice and square or miter them. I have to resort to sawhorses, some fiberboard, and an angle grinder. But despite that, I still try to do a nice job on cutting square tubing with the angle grinder. I don't try to cut through it from one side. I do 4 individual cuts after transferring the scribe line with a nice precise square all around the square tubing. That gives me, without a precise bandsaw or cold cut saw, a pretty decent cut. And also the fit up was not too terrible in the end. Also trying to clean off most of the mill scale. I know that a flap disc is not ideal to remove mill scale, but that's a 3M Cubitron flap disc, and it's quite aggressive and it works okay. And then it's just a matter of clamping everything together and welding it out. This is the cross member that the machine will sit on, and it's quite a tight fit in the frame, but nothing we can't hammer in place. I double checked with tape measure just to get it a reasonable parallel. The cross-section of the cross member that the machine sits on is smaller than the surrounding frame, because when there is oil on the machine and it's dripping down onto the cross member, I don't want it to run off the frame's side, which would happen if the cross member was the same cross-section, therefore flush with the top of the frame. Here I'm using 2 cutoffs of the square tubing and some clamps to get the cross members flush with the underside of the frame. This arrangement of clamps and the stock pulls the cross member parallel to the underside and flush. And then it's just a matter of welding everything out. I'm not the greatest welder in the world. I'm okay at TIG welding, but with stick welding, I'm always a little bit in trouble. But usually I can stick stuff together and it does not fall apart. It's nice that the frame is small enough so I can flip it around to weld always in a good orientation. I don't have to do uphill welds or overhead welds on this thing. So I can just flip it over and always weld in a good position. And here is the finished frame. It's welded, ground, and painted. It will have side panels, but those will be screwed in with some angle brackets. The holes for the angle brackets are already there. The thin profile frame beneath the machine mounting surface is for a chip drawer. The small hydraulic lift cart was more than adequate to lift the frame onto the stand. As it's shown here in the picture, with the rails, the ball screws, the X crossplate and a C-axis plate, and the table, everything together weighs about 185 kilograms. I want to make it a nice, rigid micro milling machine to replace my Sorotech CNC router. The CNC router is definitely going away. I'm going to part it out and sell off the components. The CNC router doesn't owe me anything. I have made so many parts on it and it paid numerous times for itself. But the kind of work I'm doing on the CNC machines has changed. It has gone from larger aluminum work and larger plastic work to, well, aluminum and plastic parts that are about the size of my thumb. And for that, a smaller, more rigid, and also thermally more stable frame will be very nice. The Sorotech router did definitely suffer during the day from thermal growth. The machine has really been great for what I purchased it for. It has been dead reliable. The Edding CNC controller, despite having its it has its problems, especially on 3D machining. It's a little bit slow, but apart from that, it has been dead reliable. And I'm going to keep the controller for now. The controller, I will just make this machine plug compatible. So I'm just changing out the plugs between the stepper drivers and the limit switches and the spindle, and it should work. It's already working in one axis because I'm impatient. I hooked up the X-axis to the controller of the CNC router, and I can just, with the hand pendant, manually jog it back and forth. It's moving super janky because the stepper signal on the controller and on the stepper driver are not set up correctly for this combination of everything. It's all set up to run my CNC router, and I don't want to change it just for a little test. So that's that. But it's already moving, and I'm figuring out how to hook up the motor to the stepper driver, and I'm creating something like a game plan. So the machine has a nice ground steel table with grid pattern with M8 threads. I want to put a zero clamp system on it, a ITS compatible chuck. I have a nice one from Becker Aerodertechnik here in Germany. The spindle I'm going to put on this machine is already ordered. It's a 2 kilowatt HSK 32 spindle from Spindle, which an HSK 32 manual tool changing interface. 2 kilowatt, 25,000 RPM. So here's the CAD model for the milling machine. And just to get an idea, I took the 3D model of the X22 spindle that I ordered with a ER20 collet chuck and put it onto the C-axis, and this gives me already a pretty darn good idea about the final travel of the thing. In the most upper position, I have about, let's do an inspect here, from here to the table, 216 millimeters. So I have at least 200 millimeters from the tabletop to the collet nut. Then minus the tool length, so I can work on some parts that have a little bit of height. The overall travels of the thing are, I think it's about, the travels on the thing are about 340 millimeters in cross direction. The official travels are a little bit smaller because I think they leave a little bit of margin for error and also some space for way covers, which I do not take in consideration for these measurements now. Just to give you an idea how small or big this frame is. So the table travel is about 280 millimeters. And the C-axis is about 200 millimeters. I think they say it's only 150 in the official document, and there might be a collision issue somewhere. The ball screw is long enough at least, and it could go down far enough despite crashing into this Aerovod chuck. But yeah, it might collide with my drag chain holder here, but I will figure that out. It's a nice little stout machine frame. As you can see, I already played around with the drag chain up here. And just like some people, the machine is a hollow shell of itself. They did not put the epoxy granite in the 3D model. And no, on this machine you cannot separate the gantry, the blue gantry, from the base. That's one piece. It's not meant to be taken apart. You would need an angle grinder with diamond wheel for that. But yeah, that's how the spindle will mount. And the nice thing about the Spindle spindle, it mounts from the front. They have keyholes on the back where you just hook it over some screws, and then you have this angled hole from and you can tighten the screws from the front. So you don't need an adapter plate or need to screw it from the back, which I think is quite a nice design feature. And I didn't go with water-cooled spindle. I have chosen the air-cooled variant with a separate 24-volt fan. There are a few things in the machine geometry, in the milling machine geometry, that we can check. The first and most basic thing is to check the flatness of the table in relation to the X and Y axis. That's very easy. We just put an indicator on the Z axis in this case. I have a small magnetic base here. Boop. And we can drop an indicator on the table, get it in contact, and now we can jog the table. Since I don't have motors on this machine, this is my drive servo now. We start by jogging over in the X-axis, or what will later be the X-axis. I think we went from 0 to 0 on both ends with a 20 micron dip in the center. Let's mark this down. Now we move the table to the front, means I have to reach back through the machine frame to get to the coupler. Okay, excellent framing on the video here. We're still at 0 here. Now we move the indicator over here using the X-axis again. Okay, here in the middle, we have this minus 0.02 millimeter divot again. And we're at plus 0.01 millimeter out here. Let's move it to the center of the table too, because that's kind of interesting. Okay, that's also minus 1.5. So the entire flatness of the table, as I mapped it out by now, is within minus 20 plus 10 microns. We got flatness of the table sorted out. Next thing would be the squareness of the X in relationship to the Y-axis. That's also very important. I have a reasonably accurate square here. Last time I checked this, it was basically a deviation of less than 10 micron squareness between those two sides of the square. And for checking the squareness, we put this on the table. We will clamp it down with one bolt, just so it stays in place. Brass shim, so we don't damage the square. Heavy washer and a nut. Okay, and to check the squareness now, we align one axis of the square with one of the axes of the machine. Means we get our indicator here. For those who are wondering, this tiny indicator stand is made by H&G. HG. A friend showed it to me, and I like to have a small indicator stand in addition to my large ones, and this has an excellent fine adjust up here, and I'm very happy with it. So I got it here on 40, and I'm traversing the x-axis with the cordless drill, and I'm going to bump the square Okay, that's not too bad. We start at 41. Okay, I get basically a 0 to 0 reading end to end, and this also checks the straightness of the axis we just moved. So that's very convenient. So we're double checking here two parameters. Now that we get one axis of the square in line with one of the axes, we can move the indicator over to the other side of the square and check how square the other axis to the first one is. You get probably a little bit of a parallax error because you're looking not straight on the needle, but you just have to look for movement of the needle, not the actual reading. Let's get my power feedback there. So that's a squareness of 10 micron over distance of this much. How much? 130 millimeters. So that's very reasonable. That's that's really nice. I like this. To check the backlash of the ball screw, I hooked up the stepper motor and the driver to the control of my CNC router, and I'm stepping back and forth 10 microns on the hand pendant. And that's pretty much exactly what I get on the dial testing kit measuring the actual movement of the axis in both directions. Means that there is no lost motion in backlash, or very minimal, the 10 micron indicator. and it has also a measuring error. But that's already very, very promising. The easel ball screws in my CNC router have about 20 microns of backlash, depending on the weather. These seem to be extremely tight. They are C5 precision and they are ground ball screws on preloaded nuts. So there are other things that we could and should check on this machine frame, but that's what I wanted to measure for now. I completely neglected the C-axis for now, but that will come in the future. Look what arrived during filming this video, the Spindle. This is a Spindle X22 HSK32 spindle with a manual tool change, 25,000 RPM spindle. They're made in Germany. They built the complete motor themselves, and the HSK interface in front here, this is a part from Kern. You can purchase that if you want to build your own HSK spindles. The interface and the clamping mechanism that pulls the HSK tool holder into the spindle, that's purchased. As I mentioned, they have this key slot feature on the back, so you can bolt the spindle on from the front. You hook it over the screws, and then you tighten it down from the front with a ball and Allen key through this angled slot. Most of the housing is aluminium. It's nicely machined and anodized, what you would expect. But this lower cap here, this lower end is steel. So I guess this extends somewhat into the aluminum housing, and I guess, that's a wild guess now, contains at least one of the bearing sets. Why I really bought the spindle is the HSK interface. After a few years of running collet spindles, like on my Servotech router, using 2 wrenches, tightening and loosening ER collet nuts, I decided it's time for an upgrade. And the way this spindle works, you have HSK interface and a regular HSK-C tool holder. As far as I can tell, or as far as people helped me to figure out, HSK-A should also be clampable with the system. The only difference is HSK-A has an index notch for a tool changer. And the groove for the tool changer arm looks different as far as I know. So you have a dot on here, an engraved dot. You align it with the red dot on the spindle. It goes in. Come in with your torque wrench. And you give it something like 2 rotations, and then it's clamped. And to get the tool out, you open it until you feel a little bit of resistance. You overcome the resistance, and then it gets pushed out of the taper. This is a very shallow taper, so this is extremely self-locking, like a Morse taper. For that reason, you need the force to push the tool out of the interface. But this is darn fast. And the nice thing is, with these tool holders having face contact, HSK has basically a very shallow taper. It's hollow, Hohlschaftkegel HSK. You can set it on the surface plate with this face here as a reference, and you can measure your tool length on the surface plate using the height gauge. Means I don't need a tool length sensor or tool length probe in the milling machine, removing a little bit of complexity. Okay, that's a 2 micron indicator, and the needle is jumping between 0 and 2 micron. So that's very promising already. Let's see how it behaves with a tool holder in it. And while we're here, we can take a look at the clamping mechanism. So when you look down in there, I come in from the side with the Allen key, and when I spin the Allen key, this block comes out to the side. That's a floating element in the spindle. That's really hard to show. It's this block that gets wider and expands into the back of the tool holder. And since it's floating in there, it's finding its center in the tool holder itself. That's the reason why it's floating. It's self-aligning, basically. I need a taper wiper for HSK32. Don't have one. Forgot to order one. Let's get the tool holder in. Yeah, that's about the same as in the spindle taper. That's really darn good runout for a reasonable, affordable spindle. Considering what a spindle on a vertical machining center costs, this is really a bargain. I know it's real money. I think the spindle and the tool holders were about something like 3,500 euros, including tax. But still, that's an incredible degree of precision that you get here. Of course, running the spindle will tell the whole story. Just measuring runout and things like that on the surface plate doesn't tell you a whole lot. So I purchased the spindle with 5 tool holders, and it also came, well, I also bought the torque wrench, collet nut wrench. The spindle comes with some molybdenum paste and the manual for the HSK interface. You have to lubricate the interface from time to time. That's the same as on a real VMC spindle. Also got the shielded cable with the correct plug. They have other options on RPM. I think you can get them up to 55,000 RPM, but I decided against the high RPM spindle because 25,000 RPM is usually very good range for general small machining. Not speaking micro machining, but for end mills down to 0.5, 0.6 millimeters, it's perfectly adequate, and you can make smaller end mills work on such a spindle without problems too. You just have to keep your chip load the same and reduce the overall feed. It has a 24-volt fan on it, so the cooling fan that cools the spindle motor itself is not connected to the spindle itself, so it's not spinning at 25,000 RPM. And that means it's a little bit quieter than spindles with a mounted fan. The other option would be a water-cooled version, also an option on these, but I'm always hesitant with water-cooled spindle because that's a lot of added infrastructure and stuff that will leak over time. Notice that I said will leak, not could leak. That's the reality of industrial equipment. It's not the question if it will fail, it's the question when it will fail. And when it fails, how catastrophic will it fail? So this is the motor I'm going to use on all 3 axes. It's a Lichine Easy Servo Motor, model ESM 22430. This is a closed loop stepper motor. Means it has an encoder that tells it if it has reached its final position. So closed loop system. It doesn't give you feedback of the axis position like you would have with a glass scale on the machine, but it gives you at least a feedback of the ball screw if it reached its destination, or if it lost steps in the process, or it crashed. If it crashes, it will give a follow error and the machine will e-stop. Now, that's very nice too. Problem with these motors is the connection. The encoder is hooked up with a 15-pin sub-D connector, which is okay, I think. This would be quite okay. But the motor windings are hooked up with this Molex mini-fit connector, I guess. And this just doesn't instill a lot of confidence in me hanging out in the breeze. So I figured I get some die-cast aluminum housings, and I have a terminal block in there. I cut off the wires or the plugs from the motor, run them in, and put the wires onto the terminal block, and then I can use some nice cable that can be used in drag chains to go out this box and directly onto the driver cards. I'm drilling the holes for the cable glands with a 12mm end mill because, believe it or not, I do not own a 12mm drill bit. A nice sharp end mill works quite well for this purpose, especially since the holes are not very deep and it's just die cast aluminium. The cable glands from lap cable just snap in from the outside, and then you tighten the nut from the outside. It's a fairly nice design. We used to use them at my day job a lot. Since I already had the tapping head in the drill press, I went ahead and tapped the M2.5 threads for the terminal blocks with it. Here is one of the connector boxes finished with the motor wires, motor wires and the encoder wires coming in onto the terminal block, and then I'm going out with cables that are suited to be ran in a drag chain. And I'm not stuck with the stinky little Molex connector right here in front of the mill. This is the ITS chuck that I was talking about bought it from these people, Becker Erodiertechnik. It's Arova ITS compatible. I think the patent from Arova ran out and everybody can make these now. What it is, it's a zero clamping system. Basically, you have pallets that can drop in here. Would be nice if it dropped in. That drop in, then you lock them in place. And you can do your machining on these. You can unlock it, you can take it out, put in the next one, and each one will be located 100%. Well, nothing is 100%, but very, very close. I think the XY tolerance on the ITS chucks is like 3 microns. Same for squareness and parallelism to the base. Parallelism is probably even better because it's a very simple arrangement to get the parallelism. So what that can also do, it can do 90-degree indexing. So let's say you have this standing up 90 degrees, you lock your whatever you're working on in it, you do your machining from one side, then you can spin it around 90 degrees, you lock it, then you can do basically poor man's fourth axis, relatively precise. Normally you would find this system on real CNC machines, mainly or mostly, very much on RAM EDM machines and the machines that mill the RAM EDM electrodes. The pallets locate via a stack of 2 spring steel plates. It's just those 2 plates on here, and they have rectangular cutouts in them, 4. And the chuck has these ground posts, and these are slightly larger than the cutouts. And you can see that there is a banana-shaped slot in the sheet metal, and that allows these 4 pegs to expand the square hole in the sheet metal, and this gives a very much over-constrained fit of the pallet on the chuck. And the chuck itself gets pulled down on this draw stud on this tapered section here, and there is a set of 4 balls in the chuck. When you tighten it, this is a manual chuck. There are also pneumatic ones or hydraulic, I guess. And when you tighten it, just from the side with a pin, those balls get closer to each other and pull down on this ring and pull the pallet onto those 4 pegs. And the C height is defined by those 4 standoffs. When these hit those 4 ground surfaces on the chuck, it's seated and the C height is fixed and you're ready to go. You can buy, for example, these are brass blank pallets. Usually you machine some sort of feature in it to hold your part. You can make everything an Aerova compatible pallet by purchasing the sheet metal set, the 4 standoffs, and the draw bolt. The draw bolt is the most expensive part. I think the sheet metal and standoff set is like 50 euros. Something like that. Not entirely sure. This entire system is not cheap. It's meant for real industrial use. Not for me farting around in my own shop, but there is a huge use market for this ITS system. And I figured if I get a chuck or multiple chucks, I can utilize it for myself in the shop. I want a second one for the Deckel tool room mill. And I also would like to have 2 for the CNC mill here. One over here, for example, to do face work. And the second one over here to do poor man's 4th axis work by indexing by 90 degrees. This would allow for a very, very slick workflow, I hope. But you basically have a ton of options with these chucks. That's the catalog from the people where I got the chuck from. These are standard blanks, and also this is something that's very standard in the RAM EDM world. This is an electrode holder for square, graphite, or copper electrodes for RAM EDMing. You can get them in brass, aluminum, or steel. Usually they come in sets of 12. You can get a lathe, almost like a lathe tool holder style, where you can hold a slab of material in there with set screws from the side. You can get collet chucks that fit onto it, different sizes. Yeah, collets, even more collets. These are probes. You need those on the RAM EDM machines because the chuck is not only used for, well, you usually have 2 of these chucks on an EDM machine. One on the table for the workpiece and one on the RAM for the electrode to go bzz. And on the RAM mounted one, you can use a probe to touch off your work coordinate offset. And there are also inspection arbors to find the center of the chuck. You can get a microscope for EDM machines. There are adjustable electrode holders. Well, these are less interesting for milling. This is mostly for EDM people. You have electrode holders that you can angle manually for doing sprues on molds. This is interesting. You have a 90-degree adapter here. So you put this in and you get a second ITS chuck on top at 90 degrees. So you could, instead of buying a second ITS chuck to do the poor man's 4th axis work, you could buy one of these and flip the work that way. There's also wire EDM work holding. Well, there's a lot of wire EDM work holding, and this is a larger system for 148 millimeter pallets. So you have the different chucks. These are 50 millimeter, 70, 100. This is the one I got. This takes the 50 millimeter and the 100 millimeter system, and there is the 148. These are all manually actuated. You could put this on a lathe too. Here are the draw bolts. These are fairly expensive, unfortunately. But you don't need a whole ton of them. You'd only need, these are relatively easy to change out because they're just screwed in. There is no big precision requirement when mounting them. They are aligned by the sheet metal itself. And here's the sheet metal set, the locating sheet metal. You get the 2 sheet metals and the 4 standoffs. The precision requirement for machining to mount the sheet metal to a pallet is relatively trivial. You can do it on a manual mill without a problem. I think it's like 2 dowel pinholes that you use to align the sheet metal on when you mount it, 4 threaded holes for the standoffs, and 4 clearance holes where the square peg of the chuck pokes through. And also an M10 thread in the center for the draw bolt. So that's a quick rundown of this ITS chuck system. Their special solutions give you some ideas what you can do with it. You could also put a regular chuck on one of the and put the ITS locators on the chuck so you can quick change it. That would be interesting for a lathe, for example. You can put multiple chucks onto a fixture, or you can make a magnet with the ITS locating features, or a vise that mounts to a zero clamp system like that. And yeah, I hope to utilize this in my work at least a bit, since the precision you get from this system is so good that it's basically, you don't lose any precision by using it. When you do like 90-degree indexing with it, it's usually, for the work I do, spot on. And it's relatively robust in regards of dirt. The sheet metal here is relatively, since it's a elastic deformation when it's pulled on the pegs, if there is a tiny chip, it usually gets just shoved away. And you only have to be sure that these 4 feet and these surfaces here are clean. So when it seats down, it doesn't sit on a chip. Apart from that, it's really a solid system. And it's not only for light machining, you can hog on these chucks. There is not a big deal. They are very rigid, despite looking very flimsy sitting on these 4 feet. So that's the story behind this machine frame and this machine project. I hope you enjoyed this little overview. Thank you all for watching, and I'll be back.